Hey everybody, I'm Manav, this is Shashank, and today we'll be deriving Maxwell Boltzmann's distribution. And our goal is to, make people understand such a way that they never need to, mug it up again. Because if you mug it up, there's a very high likelihood that you go wrong because you can interchange a couple of steps and the whole thing becomes a big mess. So Maxwell Boltzmann statistics talks about clustered particles. So these particles are particles like molecules, which follow cluster mechanics. And we assume that since there's a closed system where there are n number of particles, and if it's closed, the particles can't escape the system. And the bonds can have energy levels, or as we might have been taught, compartment. And these energy levels have something called degeneracy, which you might have been taught as cells. So let's start. So we can say that let the system have capital N number of particles, where n equals n1 plus n2 plus n3 up to ni, which is sigma ni, and this is equal to a constant. Now, because we want a distribution, we will talk about changes happening in the system. So the next step would be to differentiate this. So dn, which would be equal to dn1 plus dn2 up till dni, will be equal to sigma dni, which is equal to 0, because the differential of a constant is 0. Now we talked about the particles, and this is equation number 1. Yes. Now we talk about particles, we will talk about energy. So we can say that capital E equals E1N1 plus E2N2 up to EIN. Now E is the energy level, and the N stands for how many particles are on that energy level or in that energy level. So yeah, that's what the expression means. So up to EINI will be sigma EINI, which will again be a constant. Very well. So again, the same thing as the previous equation, dE will be equal to, you just differentiate, will be equal to E1 dN1 plus E2 dN2. Now we're not changing we are changing dE1 dE2 because the energy levels aren't changing. The number of particles on the energy levels are about the same. So we're going to do sigma EI dN1, which will again be 0. So we've covered the analytical equation 2. So we now have the basics to derive the expression. Now let's move on to something called thermodynamic probability, or the number of ways arrangement of the particles in the system. Now for classical mechanics, according to Maxwell Boltzmann physics, W will be equal to thermodynamic property. Yes, W will be equal to capital N factorial, that is the total number of particles in the system, the pi function Gi plus Ni by Ni factorial. Yes. So the pi function represents multiplication. Its analysis of sigma denotes addition. Summation. Exactly. Now we have something called thermodynamic property, and that is expressed as a mathematical function over here. Now what we want is a distribution. So when you want to convert a function into a distribution, we use a very powerful tool of mathematics called the logarithm. So what we want to do is we'll take the logarithm on both sides. So that will be equal to log W equal to log of n factorial. Now pause a second over there. We have the pi function, and when we take the logarithm of pi, it becomes the sigma function. Why? Because if you have log of a into p, it becomes log a plus log b. So multiplication becomes addition. So
it is log n factorial plus addition of log of g1 power n1 by n1 factorial plus so on. You keep adding them, so it will become summation of log of g.
Whatever is inside the pi function.
Whatever is inside the pi function.
Yeah. Factorial. Yes. Now we have these pesky factorial terms which are very annoying to work with because they give you ridiculously long log search, and it's very tough to compute the logarithm of factorials. So we can use a clever trick developed by Stirling, which is called Stirling's approximation, where the log of n factorial equals n log n minus n.
So we'll just apply the Stirling's approximation here, right? Log W doesn't have any factorial, so we're just going to keep it like that. Now we have two terms that we need to apply Stirling's approximation to, this one and this one. By the way, we can write this term as log Gi power Ni minus, I'll just remove this, right? Instead of writing it in the denominator.
Log Ni factorial.
And since this is the power, I can write the power as a coefficient.
Ni log Gi, yeah.
So I'm just going to erase that out. Now these two terms need Stirling's approximation because they have factorial terms. So we are just going to write it as n it's basically n log
n of
n minus n. Plus, this doesn't have any factorial term. We'll just keep it like
so keep the sigma as it is.
keep a sigma as it is.
N of Ti.
Similarly here, I'll write it as ni log ni minus ni.
So that becomes plus n. Because there's
Minus of minus.
So now we have our expression. Now, as we did in the previous steps, we need to find the change. So we'll take the derivative. So t log w and the derivative of the right hand expression. We'll be equal to, we need to split the right hand expression into two parts. T of the first expression, which is n log n minus n.
Plus, since differential and summation is, they are basically linear operations, you can swap the order. It'll be like
But first, change root. So
udv minus vd.
be careful because the signs are very fond of here. So 1 by gi into dgi
gi
plus log gi into the differential of the first part, which is dni. Now we take minus ni into
differential of
1 by
log ni is 1 by I dni plus log ni dni.
dni.
And outside we have
Plus
another dni.
dni.
So that will be dni.
Now there's a very important thing that we need to remember. Here we're taking the system at equilibrium state where log w is maximized. So the differential of log w will be equal to 0. So the left hand term becomes 0. And also the first expression on the right hand side, because n cannot change with the total number of parts in the system, the differential will be 0. So that first part also becomes 0. Now we can cancel out ni and ni. Because the number of cells has to stay the same, which means that the degeneracy, which is gi, has to stay the same. It's a constant. So dgi means a change in the degeneracy. So it doesn't make sense, so it'll be 0. Yes. Now we have a very workable expression. We have a sigma of log gi dni of minus dni minus log ni dni. Yeah, so we can take a sigma of the whole thing. So we can write a sigma again. 0 equals sigma of log gi minus log ni, because plus dni minus dni will cancel. And this whole thing is common. The dni is common. So log gi, it's log gi minus log ni. Because there's a minus sign outside.
Correct, there's minus sign outside.
So next we can use the property of logarithms. We can write log gi minus log ni as log gi by ni. Yeah.
You can write this as
Now, if you want ni in the numerator, we can take a minus sign out, and that will give us sigma log ni minus log ni by gi. So now we can take the minus sign to the other side, and that gives us plus with back. So let's not waste time. Let's write this as equation 3. Okay.
yeah. So basically, I have this expression to be equal to 0. I have equation 1, equation 2, equation 3 to be equal to 0. I'm going to take all the 3 expressions and I'm going to multiply it with some factor, right? And then that will be again equal to 0, right? I'm taking sigma dni from here, sigma ei dni from here, and from here I'm going to take my final expression, which is sigma log ni by gi dni. So sigma log ni by gi dni plus some factor times
Alpha dni
plus some other factor times beta times sigma ei dni. Right? Now since all these are equal to 0,
okay.
this thing will be 0.
Now, yes. Now we can take out dni and sigma common, but again we can just directly do our work with taking them common. So sigma is sort of like integration. It is the summation. It is adding up everything. And differentiation is the opposite of integration. It is breaking down stuff into smaller things. So technically we can just cancel them. They nullify each other. So we'll have, I know mathematicians would not like this. It's not very rigorous in terms of mathematics, but it works. It makes our life easier. So log ni by gi plus alpha plus beta ei will be equal to 0.
From here you just do basic maths, rearrange terms, you'll get minus alpha minus beta ei. You just bring these two on the other side. Now I'm going to take exponent on the both sides, anti-log on both sides. So I'll get e power minus alpha minus beta ei, and I'll take gi on the other side, right? I'll take it to the numerator. So ei minus alpha minus beta ei. Ni is equal to, right?
And that's the required expression. So it's very simple. There's no need to mark it up. You just need to follow some steps, which is you take any component, you need to define in terms of the rate of change, that is the differential, and to convert from a function to a distribution, you need to take log. And to make our work simpler, we can use mathematical tricks like Stirling's approximation and Lagrange multipliers.